So we are doing the problem min and path sum, and you're essentially given an n by n grid, and you need to filter with non-negative numbers. That's the most important part too, because then um, you could have potentially negative paths. And you want to find a path from the top left to the bottom right, and you want to minimize the sum along the number of paths. And know you can only move only down or right at any time. So the constraint is that we can only move down and right, and also that each edge, each cost essentially, uh, grid I and j is greater than 0 for all pairs of I and j. Something we should note. And with that, we see if we look at this example, we see that 1, 1, 1, 3, 1 is the actual traversal path, and they highlighted for us. And the question is, how do you do that? One immediate solution is obviously you could try to brute force your way down and kind of view this problem as a backtracking problem, and where you just start from this top left node, and for example, let me just do this. You could go here, then here, and then here, here, and then here, and to see like, oh, this is the cost of stuff I've seen so far, and then you essentially back up all the way, and you would go, maybe your first split point was here, here, and then you go here, here, and that's cost of um, 11, for example, and you see the point, right? You go here, 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 then here, here, or no, here, 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 here. Um, that's pretty much it. So you see that, and then that's like gonna be about, I want to say, almost an n squared solution. No, it might be like almost n factorial. Sorry, 2 to the n. Because you're going to have n choices, and then each of those choices have 2 to the n potential choices. So this is a 2 to n solution. So with that, we then try to think about how can we optimize this, right? And essentially, with the constraint to enforce traversals, it makes the problem. The problem with this constraint traversal, we can then view the problem to how to look at this, right? We have cost dynamics, and there's two ways to view this. And at a given I, you might want to look at the costs building the problem from the bottom left, right? If we go here, and let's make this smaller, appropriate to the size, right? Say we start our traversals here from the bottom left here, right? Get red, right? And then we go here, and then so essentially, how much does it cost to get here and here? And essentially, the cost to essentially reach I and j is the grid between I and j plus the min between the cost to reach I minus 1 and j, and the cost of I j minus 1. And right now I'm using kind of like code terms, but we could definitely make it more English-like. The idea we could make it English-like this. We say the cost to reach I j is the cost at I and j plus the minimum between the two or all choices to reach ij, for example. And that's what we're doing here. That's the English words, how you can view this, or how you could generically view this. And again, you can do the same exact thing with the forward view method, but this time we just have to reach it. We are computing it in a different order, And essentially the question is, what is the when we choose one way or the other, what does it mean to actually choose that that mean this means, right? So if we decide to do a backward view here, right, we would need to essentially make this a 1 here, a 1, 1, 3, and 7, the cost, right? It's a kind of a cumulative sum. Because these are the only ways to reach these points. So then you have 2 and 3, right? Then from here, you essentially traverse from this space on. You traverse in that space. So you initialize this subspace, and likewise here, you would initialize these two subspaces as such, and then traverse in this subspace. So let's actually code it now, right? And I'm going to use Python because I'm cheating. And we'll use the backward view, right? So this is kind of a dynamic programming problem. We essentially have zeros in times the length of grid, and I can do this. The length grid. This is the number of columns, or sorry, number of rows. And m is the length of any single row is the number of columns. Right, so we do dp equals this list times the number of columns, and then for I in range of m. Right, let me print the dp whether this is right. We can return 0 here. Yes, 3 by 3, 3 by 2, perfect. So now we have that, and we would then initialize, since we're doing the forward view, we want to essentially initialize to the first column of the rows like before. I in range n, right? So we're initializing over the rows. We will say the sum will be essentially grid 0, 0, and I guess we'll say cost here, right? And we'll say dp00 equals cost, and I could say this, I and this would be m. Yeah. And we just do this. Cost. So we're going to copy paste this and do it for n. So we have 246, perfect. So the DP is looking right. So now we initialize that cost. So then we'll do the traversal before I in range of 1 to n, and then for j in range of 1 to m. And technically, if I want to be accurate, I can do r and c here to denote that. And I can do this here too. I will say c, and then this one will be r. Right, so now I'll iterate through the rows and columns and update as such. and I have the forward view. So essentially, if we remember what the forward view looks like, the forward view looks like this, right? So I'm going to be updating my grid and stuff like this. So if we actually look at the translation for that, if we try to translate it, we say dp of RC equals the cost, which is going to be the grid R and C, plus the min between dpr minus 1 and C, and the dp of R C minus 1. And then I'm going to return the cost at the final spot. And I could do minus 1, but we'll do n minus 1, n minus 1. We missed this test case, so what would we do is if we have this yeah, I'm about plus. No need a plus. Yeah, there you go. Technically, you can remove that too as well. And yeah, time complexity n squared, space complexity n squared as well. M times n actually. So that's one way to do that. But let's revisit this idea about how we actually tried doing this, right? What if we remove this constraint of this this movement, right? What does that mean? What happens to the problem? The problem then gets boiled down to something quite interesting, right? Say you had something like this, right? Where essentially it's obviously better to snake around this wall of tens. And then here. Right? The obvious path that we would use is something like here, right? Where you want to snake. So that removes that constraint. So then the question is, how do we solve this problem? Could we use DP? And let's try thinking about it, right? If we try to formulate this problem as essentially as this, right, is that if you try formulating like this, then the question is, how do you're essentially mixing worldviews when you do this. Essentially to get this to this spot, you're mixing two means of computing this, and the answer is that you can't immediately tell. And if you think about it, how do you formulate your subproblem? Where do you traverse to next? And if you do this, DP is not possible because the problem doesn't have the ordinance, so there's no order to subproblems, and that essentially boils the problem down to essentially a generic graph problem, right? And if you think about how to solve this, right, the grid could be viewed as a bunch of nodes, right? If we just transform this, or even this guy, to essentially a generic graph problem where we essentially have this type of information. Right? Not the most aligned here, but the idea is essentially if you transform the graph into something like this, then you can see how a grid problem is a graph problem. And then you can reformate this problem to essentially, given this pair of coordinates 0, 0, how do you get what's the cheapest cost to reach n minus 1, n minus 1 essentially. And a couple ideas that we can use is essentially Dijkstra's. And Dijkstra's is just BFS with a priority queue. And you might same thing with a minimum spanning tree. If you did like a minimum spanning tree, you would have that. And but some interesting things as well is like let's examine a set of node connections here, for example, right? What is actually happening if we decide to use a node connection like this, right? Right? What would happen? Right? Say we go from here to here, the cost is what? Technically 10 to reach that, right? And then the cost of the other way is what? 1, right? Are you starting to see some interesting things here? Same thing here, but it's not 1 to 1, 10 to 10, right? Right? So you can essentially boil this problem down to something like this. And I'm sorry, this is the opposite way around. Yeah, it's still the same. So if you boil the problem down like this, then you essentially kind of have a dike. You can formulate this into a Dijkstra's, right? And you essentially will build that. Hey, given this starting node, let me queue my neighbors and see the cheapest path to reach my neighbors, right? And you see that as you build this list using a Dijkstra's, that it's um, very solvable, and you'll get essentially this snake path, right? If you use a party queue, you'll never visit these guys in the party queue, the tens, right? You'll just always be in queue, visiting ones because it's the cheapest. So Dijkstra's is perfect for this. And that's the video.